1 hour and 16 minutes or 1 hour 14 minutes. So we are going to take part of the lecture today. However, you can on Tuesday, because Tuesday is the last day before Eid. So what I will do is that I'll keep the rest of the video for you to watch anytime. So there will be no lecture on Tuesday. There is no lecture on Tuesday. I will keep it to you so that you can watch it anytime, because I think so that you need Tuesday to have a shopping day. I'm not sure. So I'll keep that day for you. So no lecture on Tuesday, but watch the rest from your side. Now, going back to what we have mentioned, chapter 12. So we are going to cover risk assessment, reliability, and something called the minimal cut as well. Now, the minimal cut, I said in the video that it is not required for you to know the minimal cut. So you will understand that. But that was for the students of process safety when I taught them. However, for you, I want to include this minimal cut as part of what we are going to study. Okay, so I think so you're ready to watch the video. It's going to have more than one concept related to the risk assessment, fault mode or fault effect analysis, and how to calculate the risk. We already took the part of the risk, but I'm taking it again here, and some other stuff related to the reliability and probability. You will like it. Okay, so let's start.
Then chapter 12, it's just a continuation of what we have taken, because it's still more like qualitative, how we look at risks and looking at the areas where there could be some problems. And in this case, we want to look at the areas that we could have high risk and some other methodologies that we could go through. Okay, so risk assessment includes an incident identification and the consequences. So how an accident occurs, and you analyze its probability, and what are the consequences. And we always represent that like this is like talking about is probability. Mainly you're talking about the frequency, like how many times does it happen? Does it happen every day? Does it happen every month? Does it happen every year? And the consequences, like is it dangerous or not? And how do we calculate this? Usually when we multiply our frequency with how much dangerous is something, and then you're going to say, well, if it happens every day, right? It happens every day, and it is very dangerous. That is something severe that we never want. But for example, it happens every year once, but it is very dangerous. Of course, this will be still a risk, but it will not be as high as if it happens every day. Now, if it happens every 10 years, and it's very dangerous, and here every 10 years and very dangerous, it just puts the risk really very low because it happens every 10 years. Now, if you say it happens every 100 years, forget about it, right? So the thing is that the frequency it will increase the risk. Okay, will increase the risk if it happens every and then. So every now and then, if it happens, it's very risky. What about the dangerous part? The dangerous part is that it may happen every day, but it is not risky at all. It is something that is not dangerous at all, which means that could be, we don't need maybe a design for that to be inherently safety, but we just deal with this. We just deal with it. So now I just said that it's not that risky. Why? Because I just said that it's not dangerous at all, even if it happens every day once. And now if it happens every 1 hour, will this be accepted or not? Now it happens every 1 minute. I know this is crazy, but what I'm trying to say that when I say it's dangerous and now I increase the frequency, I think it becomes dangerous in this case. Okay, so this is the risk where you multiply by the frequency and what are the consequences, right? The frequency and the consequences are how much it is dangerous. So, and frequency is telling you that how much it happens per certain time. And if you have a high risk, you will say, for example, it is in the category A where it is unacceptable, and then category B where it is, for example, critical, and then you have serious, marginal, negligible. Okay, and these are different from different places, so it always depends on what place you're talking about. If I'm talking about a university, it's different when I talk about an industry, right? And it's different when I talk about my shop that sells hamburgers. So everyone has its own different risks. We are going to add something. So usually this is, you will not find it in many places because they consider this as one. I mean, they more concentrate on the frequency to consequences. But operational discipline is something like you're adding if you have a bad safety precaution, you don't have good management for safety, no procedures. So you're putting this down, and this just increases the risk. Okay, this just increases the risk. But if I will talk that you have good procedures, really very good procedures, to deal with all what you have, right? So that what will happen here to the risk will go down. Okay, so that is the operation disciplines. How much you are ready for those risks? How much do you have in system, management wise, and procedures, and even the instruments, the sensors, the safety precautions, and so on. So what is the operational discipline? The personal commitment of everyone to ensure their personal and process safety by performing their tasks, so everyone knows his task or knows her task, recognizing and responding to seeking help to anticipated situations, so they know what to do when they have some kind of situation conditions. Sometimes also operational discipline is reflected as a leadership focus, employee involvement, practical, consistent with you have good procedures, excellent housekeeping, awareness, knowledge, commitment at the personal level. So that is at the organization personal level. So I think so you got an idea about OD. Of course, if you ask me what is the value of OD, always keep it as one. Because it's very difficult to identify that. Only if you have at your industry something that you can identify what is the value of OD, that is going to be different. Okay, we already explained part of that, and this is where I explained that if operational discipline goes low, the risk goes high. And this is just an example very quickly. I have any examples in my head, but it just says that if you have a very high frequency, and very high frequency usually in your head it's like once in every 2 years. High frequency once in 10 to 50 years. Moderate frequency event not expected in the lifetime of the plant. Okay. Low frequency event known to us, just to know it. So this is just numbers just tells you about what time dimension I'm talking about. Okay, so that is the equation. That is the equation that we have, and our PSM, process safety management. There are, if you compare the risk reduction efforts and evaluate it against potential business risks, and the risks we are talking about here. It could be environmental, operational, maintenance, quality, and financial. So there are many kind of risks. So it's not only risks to a person, but there are many kind of risks. And if you go to the process safety management and read about it, you're going to see the different risks that are incorporated in that standard. So that was the first part, just to get an idea about what is risk and how to calculate this. Now getting to a different view of it. Okay, so what I had explained was something very generic. Well, if you go to industries, there are more detailed definitions in this regard. And the definitions that you have in industry is something called reliability, okay? Something called reliability, this word here. It's very popular, and there have been studies like master studies and to talk about reliability and how reliable is this industry. So you can go to a certain unit that you have in the plant, and then you're going to calculate the reliability. So what is reliability? It depends on the probability, okay? It depends on the probability. So that is where it concentrates. So what is it? Let me go more into details about it. Equipment failures or faults in a process that occur as a result of a complex interaction of the individual components. So what I'm talking about failures. How much does this happen? Does it happen every year? How many equipment failures I have? For example, I'm talking about valves. How many failures I will have per year for valves? What about compressors? How many failures I will have in my compressors per year? So if you have, for example, compressors think that it is 0.1, and then you go to valves, it's 0.8, for example, or for valves maybe it's like 2.5. You will say that all the valves, they fail much more than the compressors. Okay, the valves fail much more than the compressors. Why? Because I can compare what? I can compare the equipment failure here, frequency or the probability. The data are collected on the failure rate. So we collect data to know that how much does it fail, okay? But we already know from previous experience, but if you don't know, you can collect the data and see how much it fails. The component fails after a certain period of time, okay? So you already mentioned that. This is called the average failure rate. And it's represented by mu with units of faults per time. So we calculate this failure as faults per time. The probability that the component will not fail, which is the opposite, it is given by a Poisson distribution. And this is our kind of distribution, but not to go to the details of it, this is the way how we calculate reliability, okay? So the reliability, which is something good, it is the exponential to the negative of mu, which are the faults per time. How many faults, how many failures I have per time? T. Okay, so this is the exponential of minus failure. Gives me the reliability. Now, if I want to calculate the failure probability, which is the unreliability, which we represent as P of T, it is equal to 1 minus the reliability, 1 minus reliability. So if something that is only 0.1 reliable, that is not very much reliable, right? So if it's only 0.1 reliable, what is the probability of failure? The probability of failure is very high, which is 0.9. I hope you got the idea, right? So the lower the reliability, which is something good, it's not good. And of course, this is reflected very clearly when we say failure probability, that is 0.9. Okay, failure probability. Think of it as a percentage, 90 times per 100. So the probability that we'll have failure from 100 cases are 90. So that is a very high probability. So if failure probability is 0.5, so it's 50%. So that is the meaning of failure probability. And these are opposites, right? Reliability and failure probability, they are the opposite each other. So this is how you calculate. All we need is mu. We calculate reliability, and from reliability, you can calculate the failure probability. Now, it can get complex. And in this case, I'm just showing you of the complex cases that we have. And this table, you always need to keep it in front of you because it's going to be very supportive when you try to solve some problems in this chapter. Well, what do we have here? If we have, this is the failure probability first, which is P, right? This is P, and here's also P. Here's the reliability, which is R, and here's the failure rate, which is mu. So if I start with the failure rate, which is mu, how many times per year? So if I have two failure rates, this could go fail, and that could fail as well. For example, you have two valves redundant to each other. So it could be this and this, right? Or that. And since that we have this failure rate, If you have something redundant, actually you're going to add them. You're going to add them, and sorry, it's not, maybe not the redundancy, more than that you have, for example, a valve, or you have also an alarm system here. So this could fail and this could fail. Now, this or this, they are independent of each other, but the total mu will be mu1 plus mu2. So you add the failure rates. You add the failure rates that you have. However, if you have the AND in which both of them could happen together, they are very much related. There's a different equation in which you can calculate mu, which is minus ln r divided by t. Okay, minus ln r divided by t. How did we get this equation? I mean, I will not go through the details. It's simple, you know. It just comes from the e to the power minus mu t, and you're trying to put your reliability equal to 0 and finding mu. Okay, so that is the only idea if you want to do your math there. Okay, what about now the reliability? After I get the mu, if we have an OR gate, okay, we have an OR gate, so this or this happens, they are independent from each other, not depending on each other. So you multiply the reliabilities. What do? You multiply the reliabilities. And that is the idea. So you multiply the reliability. So this is just a generic thing. And now to get this failure probability, if you can recall, what is reliability? Reliability is failure probability is 1 minus r. So it's 1 minus r1 into r2, and that is written here. 1 minus r1 into r2. So after you do your math here, you're going to get some generic thing here. So you calculate the reliability and then you calculate the probability. So if things are in series, you see here it's written, if things are in series, what you're going to do, you're going to multiply them. So if talking about reliability, you multiply them. And of course, this equation depends on what? Depends on that. So you multiply them. And if things are in parallel, now you're going to go to the failure probability. You multiply them if in the failure probability, and the opposite, you're going to write that if they are in series. So the failure of the system requires the failure of both components, right? So the failure of the system requires the failure of both components. So both of them should fail for that R to be failing. And I don't know if you recall from probabilities where you add them or multiply them. It all depends if they are dependent or independent of each other. Note that there's no convenient way to combine the failure rate. So what we're trying to say here, this is the way that we can have things. If we have things in series or in parallel, where you can calculate the failure rate, the reliability, and the failure probability. Okay, great. Just to know the values of mu that we have. So the values of mu that we have, which are faults per year. So these are how many faults per year we have. So what do we have? Just to get an idea, we need a comparison here. So control valves is 0.6 faults per year. So we are talking about how many faults? We are talking about every 2 years you're going to have about 1 fault. For control valves, like every 2 years you're going to have more than 1, 0.6 and 0.6. So that's 1.2. You're going to have 1. And this is what you're going to say. Wow, every 2 years I'm going to have only one fault. Yes, but if you have 1,000 control valves, now how many faults you're going to have per year? Oh my God. Now I'm going to have 2,000 faults per year, right? Per 2 years. And that is about 1,000 faults per year. So I'm going to have every year 1,000. And now if you think about 1,000 per year, now your head is going to click and say, oh my God, that's too much. And why it's becoming too much in this sense? It is becoming too much because if you think about per day, divided by 365, you're talking about every day you're having a fault in a control valve. So this is This is when you start putting things in things in numbers, you find out that it may become much more complicated. Okay, let me get that. So again, sorry for that. So what do we have here? We also have like we want to compare the flow measurements for fluids and flow measurements for solids. Solids, if you have a flow of solids, you always have failure much higher than the ones of a fluid. Why? Fluid is much more smooth. This one blocks and causes some problems. A gas liquid chromatography we always have. I don't know if you dealt with that, but I dealt with it, and it's crazy. If you have a chromatography at your lab, you see how many faults per year. It's 30.6 faults per year. So you're talking about like every 10 days you're having a fault. And that is true. We always have a problem and call the technician. The technician comes, what problem do you have? I just fixed it 1 week or 2 weeks ago. It's written there that these are the numbers of faults per year. We are expecting to get something like that in our life. So they are very important, but they have a lot of faults and so on. There are things which are very less of faults, like the pressure relief valve, because it is the least of in contact of our process and system or chemicals, and that is why it has the least of it. Just to take an example, so this is like an example, both systems demonstrate unrevealed failures. For the alarm system, the I just worked for the solution. So this is example 2.3. So let's go to example 2.3 and find out the problem. So before we get to example 2.3, there's one problem I think so that is good to solve, which is example 12.2. And in this case, what do we have? We have a diagram, and this is the diagram that we have where it's just a reactor. We have a stirrer, of course a chemical reaction, and we are having some kind of a switch here, and it's written A. We have an alarm set at a certain pressure value. We have a pressure controller here, indicator of course, and a controller, and we have a solenoid valve sitting here. So what is the reliability of that system that we have here? Okay, so this reactor contains a high pressure alarm to alert the operator if we have any dangerous thing, and of course we have a pressure switch, and as we said, we have an alarm light indicator, and on the other side, for additional safety, I have an automatic high pressure reactor shutdown system is installed. This system is activated at pressure somewhere higher than the alarm system and consists of pressure switch connected to a solenoid valve in the reactor feed line. The automatic system stops the flow of reactant. So it stops the flow of reactant in any dangerous pressure, if there's any dangerous pressure. Compute the overall failure rate, the failure probability. Overall failure rate, again, the failure probability, the reliability. So we want mu, and then we want P, and then we want R. And then the mean time between failures. Okay, we did not take them, but that is simple. And we are going to assume by the problem here 1 year of operation. So what do we have here? This is what we have. So now we are going to include our switch alarm and the switch for the controller here and the solenoid valve. So this is what we have: pressure switch 1, alarm indicator, pressure switch 2, solenoid valve. And from the table, we're going to see that for switches, this is the faults per year. For alarms, this is the faults per year. And for solenoid valves, these are the faults per year. So these are the faults. To calculate the reliability, we just take the exponential term and we calculate the reliability of each one. And here you can see which one is more reliable. So for example, the alarm indicator is more reliable than the rest because it has a less faults per year. Okay, less mu. Now if you want to calculate the failure probability, which is the other way of looking at it, we just subtract by 1, and of course you're going to see the one which has the least failure probability is that. So this is 0.04, giving you the idea that has least failure probability. Now I want to look at the system as a whole, right? A system as a whole. What is the reliability of that system? And then what do we have here? You can see that these things are in series. These two are in series, but this is in parallel with that. Okay, So I know that these two are in series, but if you can see that this is parallel with that, okay, so these two, like, they are parallel. So in this case, I'm going to calculate the R for each one, and then I multiply them, right? I'm going to multiply them, and I'm going to calculate the R for each one, and I'm going to multiply them. And after I get the reliability of these two systems here, what I'm going to do, because they are in parallel, now I need to go to the AND OR system that I have found out, and this is equal to 1 minus the R3. I think so, it was like that, 1 minus R3 into 1 minus R4. So something like that if they are in parallel. Okay, so this is what we've tried to do. So the first thing we are going to start, because they are in series and it's written here, these two components are in parallel. The two components, I mean, on the right and the left. For the alarm system, the components are in series. So R is equal to 0.87 to 0.96. So you multiply them. You multiply 0.87 to 0.96. And you get the value. And of course, the failure probability is 1 minus R. That's the answer. And mu is minus ln R. We can calculate how many faults per year for the total, right? So this is if we said that they are in series, right? And what is the mean time between failures? You just divide it. 1 divided by mu, you get how many, what is the mean time between failures. So from one failure to another failure, it is 5.56. Now for the shutdown system, which gets into being if that thing is not working, and I mean, if that thing, it happens that it could not withstand what is happening. So again, we multiply them, they are in series, the solenoid valve and the alarm. So you multiply 0.87 into 0.6. So you multiply them and then subtract them from 1 to get the failure probability, and then get mu, which is minus ln R because they're in series, and you get the mean time between failures. Now the two systems are what? The two systems are in parallel. So now we're going to go to the P part because it's easier, and we just multiply them because they are in parallel, and we get 0.07. And by that, we can calculate the reliability, which is 0.93. And you can see that is really good. 0.93 reliability is really good. If you want to calculate the failure rate, which is minus ln R, in the case that they are in parallel, and you're going to get 0.073 faults per year. I can't understand this in years, so I need to calculate the mean time between failures, and I get a 13.7 year. Now I understand that this will, one fault will happen every 13.7 year. So it's beautiful to look at it, right? It's just nice to calculate these numbers, and it gives you more confidence in terms of numbers that things will happen or will not happen. Okay, so that was 12.3. I saw that was 12.2. Now going down to 12.3. There are more equations here, but I did not take these. Don't worry about them now. Was it 12.3? I think that I solved 12.2. That was what meant to be then. Then I just solved 12.2, which is the example that we wanted to solve actually, because this part that I will not cover, which talks about availability and unavailability for both the alarm and the shutdown system. There is something called availability and unavailability. I did not take that, and it's just to keep easier things for you. I just decided that I will not cover that. So here I think so we meant that we have example 12.2 rather than example 12.1. So going to the next section, after knowing the failures and the probabilities, we have the inventory. So it's another way of how to know where do we have a high risk, and where's where we can know that we have a high frequency.
Okay, طبعا we already covered part of what you need to cover today, and the next part is the inventories. But just to get things straight about the reliability and probability, it's very important for us to know the word in series and parallel sometimes gets confusing. I know that sometimes it's not straightforward and it's difficult to identify that. However, there is another word that I used to use, which is independent from each other, which means that if this switch doesn't work, it will affect the other system here. Why? Because it is in series. So that if that doesn't work, in other words, if the alarm doesn't work, it will affect the switch. If the switch doesn't work, it will affect the alarm. However, if the alarm does not work in this part, which is I'm pointing at here, it will not affect the alarm on the other part. Okay, the failure here on the alarm would not cause any failure here. However, the failure in the alarm here would cause the failure in the switch as well. Yeah, so these two are related to each other. If one fails, it will affect the other. However, if an alarm fails on the left-hand side here, it will not affect the alarm on the other side. And this is where I decide that these two are in parallel. So that is the first point that I want to mention here. The second point that I would like to mention here as well is I think so there's a clearer figure here. I just want to go. Okay, I just wanted to explain what is written down there. For the alarm system alone, a failure is expected to be once every 5.5 years. Similarly, for a reactor with the high pressure shutdown system alone, again alone, a failure is expected to be once every 1.8 years. However, with both systems in parallel, you're improving things. And you're making it 13.7 years. That's the mean time failure. And imagine how much we are improving things. So you think about it, why my system becomes better. Actually, my system becomes better because if I have only one alarm system, well, because it's all because of redundancy again. So if we have only one alarm system and the switch goes off, or the alarms goes off for any reason, then your whole alarm system goes down. But if this goes down, you have a redundancy where you also can still have another alarm system, which means your system is much more reliable. Why? Because you have a redundancy. You have a redundancy in this case. So when we add redundancy, we improve the reliability of the system, which means that you're going to have less failure to your system. And that is the beauty of redundancy. And that's the beauty of how to calculate the reliability. Why? Because you can identify how you can improve the system. Now, what is the arrangement which gives me the maximum reliability? Of course, this is not a question that I'll bring in the exam because that requires a lot of expertise. But at least you know what is the meaning of reliability and how you can calculate for a system that you can see in front of you here. Of course, there are other problems we will also take to be solved. So that is an example, and there are other problems to be solved. Okay, so you already have taken about only 24 minutes within this session here, and I would request you that you watch the rest on Tuesday or tomorrow and any other time that you feel most suitable. And after Eid, we will discuss all your inquiries, inshallah. So till here, I would open the time for questions. What questions do you have? Such more questions. Okay. I thought you'll get surprised for today because it's a bit a different topic to what we have taken. And this is the second part of the quality, and this is quality assurance and reliability engineering. And this is the second part of it, which makes it more connected to chemical engineering in that sense. So you're applying risk assessment and some other tools as well. There are other tools, صراحة, I would like to give it to you, but I will see after Eid, inshallah, because chapter 11, which is something that is really good, where there's something called the what if analysis, which is also used for safety, and it's very important. And there's something called the HAZOP study, which uses the fire and explosion index. Again, it uses the same concepts of quality, in the sense, of course, you have something like a checklist. Of course, this is the reliability. It's not reliability, and it is penalty, which takes a similar concept of reliability, and you do your study, and this study that you do for HAZOP study is very similar to something that we have taken within quality. But I decided to take chapter 12 before. I would listen to chapter 11 again, and I would decide what we need to take from that chapter, because I don't want to include something that is not within the curriculum. Okay, good. That's all for today. Thank you very much, and inshallah, see you after Eid. All the best. If I will post this, inshallah, to the link.
Quality of that system.
I'll post it on YouTube. Sorry, on WhatsApp. يعطيكم العافية ونشوفكم على خير. فالله مع السلامة.